Hi, I'm Caesar Feng, and welcome to my M4 Final Hackathon discussion video. Today, I will dive deep into my stroke prediction classifier. I will improve performance on several models, and I will assess their fits and their performance, and let's dive into it. So first, my journey began with data exploration. I loaded in the training data, so around 12,000 rows with features like average age, average glucose level, smoking status, plus the target, which is our prediction, stroke, whether the patient will have stroke. And so we can see that there's no missing value from a data set and across the 12 columns. So we also have binary features like hypertension, and we also have continuous ones like BMI, categoricals like gender, and we have some highlighted unique diversities on the average glucose level, which has 3,449 unique values. And we just use the functions, duplicate the sum and is now sum to make sure we have a clean data set and to ensure a robust classifier later on after our model building. And to make sure that we will have a robust model, we can next engineer features to boost prediction quality. And also we can use scaling to make sure that our prediction variable is well balanced. So I bend age into four groups. So we have young from 0 to 25, etc., and to very elderly plus 65. So reflecting stroke risk increases with age. And for BMI, I used I used medical thresholds, underweight less than 18.5 and obese over 30, since obesity correlates with stroke. And I also scaled numerical features as age, BMI, average glucose level, and interaction with the standard scalar, normalizing them to zero mean with univariance for model building. This ensures equal feature influence importance, improving model later in convergence and accuracy. And so here in the SNS compile, we can see that we have a great imbalance, and this is a hurdle. So it shows that only 4% are strokes. So there's a severe skew. And here I used a SMOT method to oversample the minority class to 50 of the majority, then undersample to 80%. So we can create a balanced set for later model building. And it's critical in healthcare to avoid missing cases. So we should make sure that we identify all the strokes. So later the threshold tuning complemented this, adapting to this test as 4% rate. So we can discuss more on that in a minute. To begin our model, so we can actually start with the three most popular base models, which are random forest, light GBM, and also the XGBoost. So they have all pretty high F1 scores with light GBM led with 93%, excelling in both precision and recall. So this showing that the gradient boosting efficiency is very good. So the strength of the light GBM model is the speed and accuracy, and the weakness, So also light GBM minimizes the missed strokes. So false negatives that could harm patients. And false negatives are raising cost, but in the medical case, it can be justified. So later on, we will dive into the blending and hyperparameter tuning because the three models have the different strength. So we are combining them into the blended model to improve fit, also to improve our F1 score. So I stacked probabilities from random forest, XGBoost, and light GBM using a five-goal stratified cross-validation and fed them into a logistic regression meta model. So pre-bending, blending, the individual evidence scores are at most 93%, but the post-blending, it hits around 95% on the resampled data. And this is very good. I use random search CV grid lines across all models for the best hyperparameters. And the final so we can see that Light GBM is performing really well, and the tuned models recall, the blended model recall is also very high, so it's the best performance. So to improve fit for validation strategy, we are using a five-fold stratified k-fold cross-validation. So each fold is preserved to the 4% stroke rate, unlike a simple train test split that risks uneven split. This gave the model a very stable F1 estimate for blending, reduce variance, and also reduce our overfitting risk for our blended model. And I also validate performance across data subsets, ensure my data threshold choice is good and held up. For the learning curve, we can see that the light GBM learning curve F1 is near 1, and validation stabilizes at 93% of resampled data. And also, we can see that light GBM features more and stresses more on features like age and average glucose level. So the top stroke drivers. So I addressed overfitting with the blendings, diversity, and light GBM's regularization. Example, max depth it reaches 20. So this will give a really high score and prediction accuracy around the 4% actual positive rates. For the confusion matrix precision recall, after tuning and blending, so the threshold is set to 0.8, testing 0.3 to 0.7 via cross-validation, hitting 5%, around 5% of positives. And this tuning balance catching strokes with manageable over-diagnosis, optimizing practical value in our medical case. And also, for future improvements, we can say that I will probably get some data from outside sources on diet and exercise data, and probably from health surveys. These lifestyle factors hide the stroke risks, and I would also experiment with stacking more models, such as gradient boosting variants, and to achieve some with some lower learning rates. For example, 0.001 for finer conversions. Feature-wise, principal component analysis will reduce noise if multicollinearity exists. In production, I monitor F1 weekly, retaining if average glucose level drifts more than 5%. And this is our final prediction model. And thank you for watching.